Hello everyone, my name is Taeyoon Kim. Today, I'm going to talk about... Timer does not work. Fine? Okay, then I will restart. Hello everyone, my name is Taeyoon Kim. Today, I'm going to talk about how to improve failure handling of deep learning job failure on shared GPU cluster. This work was done on collaboration with Suyeon, Jeong, Jongseop, Soobee, and Myeongjae at UNIST. A shared GPU cluster provides hardware and software to various users for deep learning model training, and these users can take advantage of several functionality provided by this infrastructure, such as resource scheduling, storing data in model, and handling the failure. This shared GPU cluster is now commonly used to run their workloads in many companies such as Microsoft, Amazon, and Google. In this shared GPU cluster, one major source of resource inefficiency is unsuccessful job completion due to the job failure. Job failure occurs during daily training, and this job failure results in a waste of GPU resources used until the failure occurs. Previous studies focus on workload characterization and discuss how this failure affects the cluster utilization. They found there are many types of failure in shared GPU cluster, and it is hard to generalize and categorize the failures based on each reason for the failure. Our research differs from this study in that we present an actual method to leverage knowledge from prior works. So, the key research question is, how do we deal with various failures to enhance the cluster resource utilization? For failure handling, we can largely classify all existing job failure into two categories. First, deterministic or DT failure, and second, non-deterministic or NDT failure. DT failure is repetitive, so it will repeat with retry failure, such as syntax error and corrupted data. On the other hand, NDT failure is transient and can be overcome with retry failure, such as transient network failures. Now, let's look how existing shared GPU cluster handle failures in the presence of DT and NDT. When the user submits the training job and the job is scheduled, the cluster manager places the job onto the cluster execution. Now, let's assume that training fails before job execution complete. The existing approach takes simple heuristic to handle this failure. The first approach is performing a fixed number of retries on failed job. Philly, Microsoft Cluster Scheduler, has this kind of handling strategy. This can increase the job success rate by retrying NDT failures, but it wastes resources by retrying DT failures. The other approach commonly used in practice is simply terminating failed job. This can avoid the worthless retry on DT failures, but it sacrifices the job success rate by not retrying NDT failures. Our work, Sibylla, can differentiate DT and NDT failure, and with Sibylla, what we want to achieve is no retry on DT failure and retry on NDT failure. As the figure shows, Sibylla has a classifier, and it receives a log information of failed job log and determines the failure type, deterministic or non-deterministic. We set the two design goals as two parts. First, it must be accurate in distinguishing failed job. Also, second, it must learn various logs continuously without human intervention. Before showing how to do this, let me first describe workload characteristics from Microsoft Philly trace to reveal the opportunity. Because the time constraint, I don't explain trace itself in detail, but from the trace, you can show how many jobs experience DT failure and what is the portion of GPU hours used for retrying those DT failures. They are showing in the left and right figure respectively. X-axis shows the number of GPUs requested, and Y-axis shows the portion of corresponding failed jobs on requested job size. By this analysis, 5 to 23% of jobs experience DT failure, and second, GPU hours spent for retrying those DT failures as much as 12 to 20%. So we conclude classifying failures by Sibylla into DT and NDT failure can save significant of GPU hours not wasted on frequent DT failure. Given this opportunity, for the rest of the talk, I will cover the two design goals in more detail. First, how to build an accurate classifier. While there are several possible ways to construct a classifier, we employ a RNN model-based classifier as it is more amenable to determine DT or non-NDT failures from textual job log information. We use standard error stream of training jobs directly into stdout and stderr log files. As explained in many preceding researches, every software stack uses these error logs to record execution status and error-related information. And DL training workload is no exception in this part. So let's take a look at this example. This log data shows the code stack of prior to triggering an error in the blue color and the reason of the failure in red color. One of the main challenges is that log format is unstructured and become diverse over time. This makes a static way, like grab on log data for specific keywords, impractical in the long run situation. And this is why we make an automatic machine learning using approach. Since the log data is highly unstructured, the failure classification needs to polish the log with preprocessing stage. This is how to transform a plain text log before training. First, the log sequence from each failed job log is parsed into the structured format with evaluating the redundant messages. After that, these structural logs are transformed into semantic vectors to train the model. These semantic vectors are calculated not only by the word in the parsed log, but also by its significance by weighting term frequency, inverse document frequency technique. This preprocessed log is used for training model in Sibylla. At first, Sibylla needs initial training phase with collected log data. This data needs labeling by domain expert. Since Sibylla has auto-labeling process, we think idly this is the only phase that human intervention is needed. We plug in two RNN models, LSTM and GRU, that are specialized on processing the sequencer data. We also made that Sibylla can plug in more models so that it can feed on the change of DL models. Now, I will go to explain the second part of Sibylla, how to update the classifier without human intervention. With human intervention in updating model, needs cumbersome process to build a new training dataset with labeling process. To address this issue, we plug auto-labeling mechanism by using classifier decision on labeling data. After Sibylla decides the failed job is whether DT or NDT, the classified instance is fed into training dataset with a label corresponding to Sibylla's decision. This auto-labeling phase makes Sibylla's subsequent training can proceed in an online manner. Therefore, the decision by Sibylla is important because misprediction in one step leads cascading effect to Sibylla's future performance. To address this issue, we adopt a strategy where the classifier decision made by majority voting from multiple models. Let's recap the scenario on top view. Here's the job placed onto the cluster and the job fails. The cluster manager corrects the fail log data, and this fail log data is fed into Sibylla, and Sibylla sends the decision to the cluster manager. Based on the Sibylla's decision, the cluster manager decides whether to kill or retry the failed job. Now I'm moving to the evaluation. Since there is no available dataset for DL job failures, we constructed dataset for our study with 97 logs from data center operator and 159 logs from manual collected by Stack Overflow. We text augmented the dataset for more diverse scenarios. In the evaluation, we go over 8 training rounds to show how well given classifier incremental update. We start with 20% of labeled dataset at round 1, representing the initial training phase in Sibylla. Afterwards, we add 10% of each round auto-labeled by classifier, representing continuous updating without human intervention. For comparison with Sibylla, we use a clustering method that is represent a non-machine learning approach, each of 2 RNN models as a single model, and lastly, the oracle, which always use ground truth label. The first question for evaluation is, can Sibylla classify failure type well? This is the result of NDT failure classification performance from round 1 to 8. Precision is showing the precision and recall as a metric. The performance of single RNN model use case is better than clustering method, especially in recall, but both LSTM and GRU model are suffering fluctuation as clustering did in precision part. However, Sibylla performance is more stable than other comparisons on both metrics. For the last round, Sibylla achieves the highest performance compared with other approaches. Also, it is almost the same as the Oracle case. DT failure classification case performance also shows same tendency, so Sibylla's classification performance is consistently high and comparable to the Oracle which used ground truth level. The next question is, can Sibylla improve cluster efficiency? We simulated based on trace from Microsoft Philly, and the simulator is from preceding research. We simulated 3 policies, smallest job first, and 2 recently proposed policies, DRAS and GTINs. The cluster simulation has 200 machines, each have 8 GPUs. We have 2 competing policies, Oracle, which have 100% accurate prediction, and full retry that retried jobs with fixed number of times like Microsoft Philly. We calculated Sibylla performance in risk prediction applied to randomly chosen job. We measured average job completion time as a metric. Compared with the full retry case, predictive retrying improved 15.4% for SJF and 6.5% for DRAS and GTINs. Also, compared with the Oracle case, the performance is only worth 1%. The last question is, can Sibylla maintain high job success rate with predictive retrying? When misprediction happens in NDT failure, some NDT failures are killed without retry. This affects the job success rate. Since Sibylla's prediction is not 100% accurate, I'm showing the effect of Sibylla on job success rate here. Compared with the full retry, which achieved the highest success rate, Sibylla's success rate is only 0.06% lower. So in conclusion, Sibylla can provide higher job success rate while reducing resource waste. So today, I presented Sibylla. With Sibylla, we can only retry on failure when the failure is repeating. Sibylla is highly accurate in classifying such failure, and through simulation, we show that we can actually improve cluster efficiency. This is the end of my talk. Thank you for listening, and I'm happy to take a question.